for making this possible. Okay, so what's the most important thing about this paper? Firstly, why should you spend 20 or 30 minutes on this paper? Well, it's got the most interesting training process that you would have come across uh, if you were in 2017 or 2018. Okay, it's got a two-step training process. The first one is it's got something called unsupervised pre-training, and the second step is supervised fine-tuning. Okay, so until now in the first class we talked about transformers. We said that they have attention inside them. We spoke about the attention mechanism. We have gone over vectors. We have gone over the BERT model, which takes sentences and tries to encode them. But now we are looking at generating text, generating outputs. Okay, we are no longer just thinking about encapsulating them. We are thinking about how can we predict the words of a given sentence. That's the best part about GPT. This is what it does. It's generative AI. And you have a step called unsupervised pre-training. If you look at the diagram, which actually enables this, you'll be surprised that it's literally the transformer again. It's just the transformer with the decoder. So let me open that too. Look at this. The left hand side is what we call an encoder. This is something we went over in the last class with BERT, right? Which is a sentence encoder. This part we have gone through. This on the right hand side has an embedding with a masked multi-head attention component. Then we have add and non, multi-head attention, and so on. Now look at this. Text and position embedding, masked multi-head self-attention, layer norm, feed-forward neural network, layer norm, and finally some sort of output. So if you just take the right-hand side of the transformer, then you have GPT at a high level. Okay. So that's what we are looking to understand today. How does this model work and why does it work so well? So, okay, what we are going to focus on today though is this word masked. Okay, can anyone guess what that means? Why is it not self-attention? Why is it masked multi-self-attention? This to train your model. Okay, so let's say we tell the model we have the word I, predict the next word. If it says was, great. If it says am, okay. If it says eat, that's actually okay again. So there's many possibilities here which are fine, which are acceptable. What we are focused on then is asking the model, with what probability would you have predicted this word was? If this is close to 1, we'll be happy. But if this is close to 0, then we'll penalize you. Okay, this is how we are going to be setting our objective. Our objective is that in the output, if we take the entire English vocabulary and then find the probabilities of each of the words that you could have output as a model, I was, I am, I eat. I am just going to look at the actual word was. I'm going to come here and see what was the probability of you coming up with this word. If it is close to 1, I am happy. If it's close to 0, I'm upset. And what does this mean? I then backpropagate these results to change the weights of my neural network. Okay. Once I have this I was, now I take this as my input and I say find me the next word, feeling. So when it comes to feeling, I again have the entire vocabulary of the English language. I have the input words, I was words, but feeling also comes somewhere. And I look at this index. If this is close to 1, if the probability of the word feeling being output is close to 1, I'm happy. I backpropagate that, saying that the weights are perfect. Otherwise, if I get something close to 0, I penalize the model. This is not good. And in this way, you can see that when I go to I was feeling as an input, then the model, because it's having its weights updated with every backpropagation, is probably going to come up with under. Okay, the probability of this is now better because the model is being trained again and again and again. I was feeling angry is also another possibility. I was feeling happy is another possibility. Under is another possibility, and so on. The model is being trained on every step because we know the next word, but we are feeding in only the first few words to the model. Is our training system, it's not exactly unsupervised, right? It's, you have an output which you can check against. When you have the first two words, I was, you actually know the final answer. The next one should be feeling. But the thing is, the model itself is doing this for you. There's no human which is telling you, oh, you should have thought of feeling. So that's the reason why it's called self-supervised. It is supervised learning, but by the model itself. Till now, what does it do? It just understands sentence structure and sentence construction, you can say. This is what it learns here. So Ankit is asking, after every word predicted, will we also backpropagate to update weights? Absolutely yes. Let's look at the transformer architecture and especially the decoder part. We have something here which is the embeddings. Okay, initially you have tokens, then you have the embedding, then you have attention, then you have something called a feed forward neural network, and then you have the output. Now your output is basically a list of probabilities for every word in the English language. When you get this output probability, you check with the actual word which should have been output. If this is, so you take the log of this probability and you take the log of the actual one, so that is basically, you take minus log. Okay, what should have been the probability? Log of 1. Log of 1 is 0, so this is ignored, minus your result, log of let's say the probability was 0.7, log of 0.7 is going to be taken here, negative of that, and that is going to be backpropagated throughout the network. The feed forward neural network, all of the weights inside the neural network will be updated. You'll go through the the attention. Here you have weight matrices. They will also be updated. Your keys, queries, values will be updated. In fact, even your embeddings will be updated. There's a neural network which does this for you, and this is also changed. Okay, so for every token, step by step, we are going through this update. And this is where the secret of masked attention is. Can anyone look at this and tell me what's wrong with it? If I have to fire a token every time, I have to get a backpropagation, how much time is it going to take me for 1 trillion tokens or something? Even with 1 billion tokens. If I take 1 billion tokens, that's 10 raised to the power 9 into the amount of time for one iteration here. I'm assuming there are millions of weights in total, attention and feed forward neural network. So if I take 10 raised to the power 6, this is already a completely intractable number. It's huge. So training models is going to be very, very, very expensive. So what do we do? Think like software engineers at this point. Assume that optimizations exist, but think about architecture optimizations at this point. Okay, let's go for the sentence, is there a way to speed this up? Let's just take the first word is, and then we take the next word there, a way. I'm just creating the attention matrix. Is there a way to speed, okay, this up? Let's look at one of these words, speed. Um, if I take the first word is, I get the relation between is and speed. I take the second word is there, okay, I get this relation. I'm getting these relations, I go all the way to speed. Now what happens if I ignore this word and ignore this word? The result of this is that this row is telling me all of the contextual information that the word speed has with preceding words or preceding previous words. Okay, look at this row. I got rid of the words after speed, this and up, and what do I have? I have is there a way to speed this up is no longer my sentence. I am looking only at the word, the words before uh, speed. Okay, why am I doing this? Let me take this row and multiply for it. Then we are trying to predict the next word. Okay, in the attention matrix we were earlier filling in all n cross n values. Now we are just filling the word with the context of the words before it, and the outputs then of each of these rows, you can assume, will be outputs where the context from future words is not picked up. We are just going to look at the sentence up till this point, derive as much context as we can, and predict the next word. That's the reason why we have masked attention. Okay, in this column, or sorry, in this row, is there, these are the only two words that we can look at. When we get rid of all of this attention, if we set these values to 0, then the resultant vector of this is going to be is into some value v1 plus there into some value v2. If I had taken the other words here way up, then I would have added those values to v3 a plus way into v4, but I don't want to do that because that will give me context of future words. I just want the context of words before it, and then I want to predict the next word. At a high level, what the attention mechanism was doing was trying to gather context from all words in the sentence. I am only taking the ones which appear before the given word. And the reason I'm doing this is because I'm trying to predict the next word without looking at the next word, without deriving context from the next one. Is this making sense? This is the reason why we are masking out the values from all future words in this attention matrix. I mean, basically you can't get context of future words. You take the context of future words and you set it to 0, which makes each of these vectors like small stubs which have context from previous words only. Every prediction from this point, I'll mark this in a separate color, every prediction from this point is going to be like predicting by looking only at these many words. Okay, I'll tell you the rough output of this. You basically have a n cross n matrix where only half the values are filled. When you multiply this with value vectors, this matrix with value vectors, you get n vectors. Initially you had n words, right, in your token. You get n plus 1, or n vectors rather, which have contextual meaning of all words before them. So finally what comes as an output with n vectors that have contextual meaning before them is you have n predictions now of words through n vectors that have contextual meaning before them. I know it's a lot of text. The basic idea though is that I look at a word, I split it into pieces, I take one by one all of the words and pick up all the context from previous words. So that gives me n of these vectors, contextual. And then using that, I make predictions. For each of those n vectors, I make prediction. What will be the next one? What will be the next one? And that helps me train the model to make predictions. It makes n predictions together, not one. The earlier problem we had was per token, we could make one prediction. Now we are feeding n tokens in parallel. In the output between masked self-attention. Okay, the main difference between masked self-attention and plain self-attention is plain self-attention tells you every single word having full context of all the words around it. So imagine I could look at this word there. This is usually how humans also do things. They look at the word and they look at all the words before it and they look at all the words after it and they get context of the word there. This would be normal self-attention, plain self-attention, where you have full context. But when it comes to masked attention, it's like until now I have read only this much of the sentence. What is the feeling I'll have until now? So that output will be get context from all words up till this point. Why don't we use normal self-attention? Why do we use masked self-attention for training? Because we are trying to make the model predict the next word. We are not asking it to summarize the entire sentence, not give us maximum context, but we are trying to make it predict the next word in the sentence again and again and again. So is there, and the next word should be A. To do that, we cannot tell it that, take context from A also, because then the model is just going to take context from A and say, oh, the next word is A. No, so we try to hide this. We try to hide all the stuff ahead of it. And we say, what word would you predict here? Just by masking attention, we are able to get rid of all the context it would have derived from the words in the future and therefore stop it from seeing the words in the future. We force it to predict what will be the next word. And so you take this contextual vector, these weights, you add it to the original vector. So in this case 2, You add it to this, and then you predict what comes after 2. If it says speed, great job. If it doesn't say speed, not very good. The result of the attention mechanism in our case is not one vector, it is n vectors. Each of these rows is like an input. Masked attention for training models will be done when a model has already been trained. So masked attention is done during training and after training also. This is a very interesting point about masked attention, which is when you're training the model, you are using masked attention, that's fine. But then the question comes, hey, when I talk to ChatGPT, what it effectively does is it takes the entire sentence and it predicts the next word, attaches it, and then takes the entire resultant sentence, predicts the next word. So do I need masked attention there? The thing is, because you have trained the model in such a way, because you have set up all the weights of your attention matrix or feed-forward neural network in such a way that it expects that half the matrix will be masked. So during inference time, during actual production usage also, you will use masked attention only. That's the weird bit, because all of the weights have been updated in such a way. You might have trash weights over in the masked area, so you don't want to mess with the model during inference time. You keep the attention matrix masked. During training, you need it. During actual production usage, you don't want to update the weights. You don't want to mess with it, so you keep this masked attention. Okay. Right, folks, I hope this helped understand how GPT works. Just one component actually. The paper is a bit involved. I don't think we were able to get into anything except masked attention. But I hope that this itself is a step forward. Right? We have spoken about attention, how it works. We have spoken about what vectors are. But in this one, we spoke about what is masked attention. And just this simple word, just this simple technique actually helps make the model predict things. So all predictions actually rest on this mechanism. It predicts efficiently, comes up with n tokens together. So training is fast. Inference is still as slow as ever, but our training has become super fast. Yeah, Sarvajit, all this is just for predicting the next word of ChatGPT. But as you can see, I mean, as you can see with the valuations, or as you can see with your daily use also, it is worth it. When you do this trillions of times, uh, the model becomes really, really smart. The weights become really good. They update themselves very well. So this pink block is what we have gone through today, right? We have gone through uh, the orange block, which is embeddings. We in the pink block we went through attention, just this word, and today we have gone through this word masked, and next we are going to go through multi. So we are going through it really slowly, but I think the depth of understanding is good. Okay, any final questions, folks, before we call it a day? Okay, thank you everyone for coming. It was wonderful to have you all on Saturday morning, and thank you for being so patient with the initial audio. And Sarvajit, the next class is on Saturday again at 9 a.m. I'm going to be looking into multi-head attention. Then we'll look at the why. Why is multi-head attention being used? What does it end up doing? And yes, the recording will be shared, Nishant, with everyone. It will be on YouTube. I'll share the link. I'll edit it and have it shared. Thank you, Winnie, for the amazing questions and the help around, all over actually, not just the questions, but also when we had technical issues. Thank you, everyone. Chandrasekhar, Ibrahim, uh, Arpan, Ashish, Gagan, Jaya, Lucky, Misha, Mohammed, and Laveen. Thank you everyone for coming. It was wonderful, and I'll see you in the next class, which is on Saturday 9 a.m. Oh, also we have, at Interview Ready, I am coming up with these lectures in detail. Uh, they won't be live sessions, they will be recorded sessions, and they'll be out on the 3rd of June. So what I'll do is I'll keep you guys posted around the course. Maybe I can just share I can share the course outline with you here in the last few minutes, completely unplanned. But what we are covering in this course is vector databases, what vectors are, what embeddings are. We'll have some coding assignments here and there. We'll have the idea behind how vectors are created, how are objects converted to vectors, the similarity measure of vectors. So how do you find whether two vectors are similar to each other or dissimilar to each other? Is apple similar to banana? Yes. Is apple similar to Microsoft? Yes. So that is something which is coming up in the course that I'm creating. Vectors, how are vectors compressed? So quantization techniques, codecs. We'll also be looking at indexing of vectors. Like you have database indexing, you know, uh, you have these B trees and log structure mer trees. Here you'll have different types of indexing for vectors. So I've gone over that. I've taken a case study of Milvus DB. This is the open source vector database, looked at its internal architecture. We also have large language models. Without that, you can't, have an AI course on LLMs. So what is a large language model? What is RAG? This is on the engineering side of it. Part 2 is engineering side. There's prompt engineering, knowledge graph, how do you avoid hallucinations, what kind of fine tuning you can do as an engineer. And finally, we have part 3, which is what we are touching on right now. We have the attention mechanism. Okay, in terms the core of the LLM, how does it work? What is the transformer? What are optimizations like KV caching, mixture of experts, page attention? These are all like really hardcore optimizations inside the transformer. As engineers, we'll probably not deal with it, but it's good to know how it works. And so if anyone tells you that, do you really understand how the LLM works? You can say, yeah, I kind of do. So like load balancers, initially you might not know how they work, but as you go through this material, you understand the workings of them. So that's what we are going to go through in this section. We are going to look at various trade-offs of quantization. You have, like we were talking about multi-head attention. So there's various other forms also. There's multi-query and group query attention also. So it's a very exhaustive course, actually, to be frank with you. It goes through some the latest techniques also, papers from 2018, 2019, 2020. Okay, and then we go through again a revision of the transformer. We go through reasoning models. Without this, again, O3, O1 would not make sense. And we are going to look at how reinforcement learning, chain of thought, and scaling test time compute actually helps reasoning models. So we'll understand the underlying algorithms, the reason why the model comes up with intelligence. Okay, self-consistency is one type. Okay, and then there's the conclusion. We are looking at the future here a little bit, and yes, some case studies to keep you occupied for the next few months, if possible. You might want to design something in the end. So yes, this is at a high level what we are going to be going through in the course. And you can let me know if you have any thoughts on this in the comments. I won't take any more of your time, but thank you everyone again for coming and making this possible. See you. Have a great day. Take care. Bye-bye.